Hello, these are solutions to recitation activity 5. So we have a question here that is, which reaction absorbs heat and is hence endothermic? Endothermic is defined as a reaction that has a positive delta H. So think of the enthalpy change of the reaction. If the reaction absorbs heat, we call that an endothermic process. Now let's think about combustion reactions. Combustion reactions by nature take place with a flame. They take place with an explosion or combustion. By definition, that explosion or combustion flame for those reactions is the releasing of energy from those reactions. So they're releasing heat. So by nature, combustion reactions are in the exothermic side of reactions. If we think of phase changes, if I have a solid like ice, it's going to have to absorb energy in order to melt. So we have to warm the ice up, then it melts into liquid water, keep warming it up, keep adding heat. Eventually we can boil. And so this process here has to have the absorption of heat, delta H therefore greater than 0. If we go backwards, if we go from gas to liquid, liquid to solid, that this process here has to lose heat. So here we have to have heat being dropped. And so if we go from gas to liquid, liquid to solid, then those are exothermic reactions. So we can understand phase change signs just from the act of, boiling is liquid to gas. And so we have to add heat to the liquid to get it to boil. So that has to be an endothermic process. So 2 would be endothermic. Question 2, a chemical reaction that warms up its surrounding. So the surroundings are increasing in temperature, which means that the temperature of means that the heat of the surroundings must be increasing. So the temperature of the surroundings goes up, means the heat of the surroundings goes up. And so the type of reaction that causes the surroundings to increase in temperature is one that was exothermic. So an exothermic reaction where we have a negative sign for delta H implies that the reaction loses heat because our reaction's heat is the opposite sign of the surroundings. So if our reaction lost heat, the heat goes to the surroundings. So the surroundings goes up in temperature, it's because the reaction lost heat. So a reaction that loses heat, where did it go? It goes into the surroundings so that the surroundings can increase in their temperature. So exothermic and negative sign of delta H. The complete combustion of ethanol proceeds as indicated below. So we have an indicated delta H for the process here. How much heat must be absorbed or released when 2.5 moles of ethanol combusts? Well, according to our combustion equation here, our balanced reaction, when 1 mole of methanol combusts, that minus 555 kJs of heat is changed by the reaction. The reaction would lose 555 kJs of heat for every 1 mole of C2H5OH. And so I'm just looking at the coefficient here, and that's moles. So look to the coefficient, assume it's moles of that substance. Different problem, but it would be minus 555 kJs for every 3 moles of O2 that react according to this reaction, for every 2 moles of CO2 that are formed, or for every 3 moles of water that are formed. And so the way I can solve this problem here is how much heat is absorbed or released. This is an exothermic reaction, so heat is being released by this reaction. So how much heat? My Q reaction, I'm going to take the 1/4 of a mole, and just for every 1 mole of C2H5OH that reacts, has a Q reaction of minus 555 kJs, and so that will be 139. So the reaction loses 139 kilojoules, so it releases 139 kilojoules of heat. Heat's absorbed by endothermic reactions, which this isn't, and then we just have to cancel out our moles and then get our heat per mole from the balanced chemical reaction. Question 4, if we know water solid to water liquid, so that's ice melting, we know that the melting of ice is plus 6.01 kJs, which makes sense that that's endothermic. Ice has to absorb heat to melt. What is the enthalpy of the below reaction? So I flipped the reaction to liquid to solid. So the delta H, since I flipped it, would be minus 6.01 kJs, but I also doubled the coefficients. And so then times 2. So it should be minus 12.0 kJs. So again, if you flip a reaction, you flip the sign. If you double the coefficients, if I just double both of these coefficients in this reaction, then that would be plus 12.0 kJs, because I'm just multiplying 6.01 times 2. And if I flip it, flip the sign. Which statement is true when ammonium nitrate is dissolved in water according to this equation here? So we see ammonium nitrate goes ammonium plus nitrate, delta H is positive 25.7. That's obviously an endothermic reaction. So when this compound dissolves in water, the reaction absorbs heat. Where does it get the heat from? It's the heat from the solution, the heat from the surroundings. So the heat of the surroundings drops because the heat of the reaction here is endothermic and increases. So my Q reaction, despite, whether it's exothermic or endothermic, the heat of the reaction is always the opposite the sign, the heat of the surroundings. So a reaction that absorbs heat gets the heat from the surroundings. The temperature of the surroundings, therefore, has to drop. So the solution temperature should drop because because the reaction absorbs heat from the solution when it takes place. So remember, the temperature is dropping not because of the reaction absorbing heat directly. Like when we put the thermometer on the reaction is, not being touched. The surroundings is being touched. So the thermometer is part of the surroundings. The solution is the surroundings. The surroundings are dropping in temperature because their heat has been lost by the reaction that took place. Consider pieces of iron with solid with given specific heat, aluminum solid with a given specific heat, each at 100 degrees C, with equal masses of iron or aluminum added to separate containers with equal amounts of water. So equal masses of iron and aluminum are added to separate containers with equal amounts of water and temperature. So we have hot pieces of iron and aluminum, both at 100 degrees C. So we're going to put iron into a container of water. And then, so we're going to put iron into here. Then we're going to put aluminum, same mass, into the same amount of water. And then we're going to ask the question, well, which statement is true about the change of the temperature of water? So would iron cause the water to have a greater increase in temperature, or would the aluminum? Or would they, one of them cause water to drop in temperature? Well, obviously we're going hot piece of these items into cooler room temperature water, so the water temperature is going to increase, not decrease. So it makes no sense that adding something hot to something cool will cause a decrease in temperature. And so we get a temperature increase. And then will we get a greater increase from iron or aluminum? Which one has more heat to lose would be the question. Aluminum had to absorb more heat in order to increase its temperature to 100 degrees C. So if we're tracking how long this might take, it probably took aluminum a little bit longer to come up to 100 degrees C than iron, but they both get to 100 degrees C. So just picture putting a test tube filled with a piece of iron, and then put that test tube into a water bath that's at 100 degrees C. And then that water bath and that piece of iron will eventually equilibrate to 100 degrees C, and aluminum will too. And just probably will take aluminum a little bit longer because it has to absorb twice as much heat. So aluminum has more heat to lose into the water. So the aluminum is going to increase water's temperature by a greater amount than the iron will. Now you could put numbers to this. You could, do 10 grams of iron into the 100 grams of water. We did that in class. If you remember, it's 25.8 degrees C. And then you could then do the same problem with 10 grams of aluminum, but double the specific heat into water. I don't think I can quickly do the math on that, but my guess would be that it will go to about a temperature increase instead of 0.8 degrees, probably about 1.6 degrees. In fact, I'm going to hit pause and just work that problem out and just show the solution here. So in a minute, as you're watching the video, the answer will just pop up here in a second, but I'll go through the math and see what that will equal to. Okay, and so I just wrote out the math here that you can see that our TF for aluminum ends up being 26.6. And I just used the same numbers of 10 grams of the 100-degree iron from lecture. We saw that this increased the water to 25.8 degrees. We double the magnitude of the CS, and we get about double the magnitude of temperature increase. So we get a 26.6 degrees C. So aluminum has more heat to lose into the water, so the water temperature increases by more. And we can work out the numbers if we want to. So we can do this numerically, or we can just do it by sort of thought analogy. Okay, question 7 gets into a calorimetry question. So we have a coffee cup calorimeter, 150 grams of water, 25 degrees C. We had 12.5 grams of cesium chloride. Cesium is just a alkali metal, given molar mass. Also at 25 degrees C, it's added, dissolves in the water, leading to a final solution temperature that goes up to 32.82 degrees C. Temperature of the solution, which is the surroundings, increases. So the temperature of the surroundings increases, so the heat of the reaction had to drop here. And so this is an exothermic reaction. The sign on delta H should be negative. Calculate the heat of solution of reaction inside this calorimeter. So calculate Q reaction in kJs, and then the enthalpy of the solution process of the compound of cesium chloride in kJs per mole. And we're assuming the specific heat of the solution is just that of water, 4.184. Okay, so the heat change for the reaction, which we want to find, is the negative heat change of its surroundings, and then the surroundings is the solution. And so my solution is described by a negative MCS delta T for the solution. And so when I plug in my math here, I go negative mass of the solution. The solution is the water plus the cesium. So that would be 162.5 grams. So we do the solution mass because that's our surroundings. We assume the solution has the same specific heat as that of water. And then multiply by my TF minus TI, final temperature. Both in degrees C. So that's 7.82 degrees C. Now again, I keep canceling this intentionally so that you see a delta T in degrees C is equal to a delta T in Kelvin. So this would also be 7.82 Kelvin if you want to make sure to see why that cancels without needing to double convert our units or anything crazy. So just take the simple difference of temperature in degrees C. That's the same delta as if we had converted each temperature into Kelvin, then taken the difference. Then my grams cancel, my degree C cancels, and I get joules here. Let's do the conversion into kJs. It's a give Q reaction in kJ, so I just divide by 1,000 here. So I do 162.5 negative grams times 4.184 joules per gram Kelvin times 7.82 degrees C or Kelvin, and then divide by 1,000 to go to kJs. That's negative 5.316 kJs. We'd be good to 3 sig figs here. So negative 5.32 kJs is my Q reaction. So that's the first part of the question. The second part of the question, the enthalpy of the solution process of cesium chloride in kJs per mole. How do we get there? Well, my delta H for the solution process would take my Q reaction and divide it by however much reaction took place. The limiting reactant would be the 12.5 grams of the CSCl. And then we just multiply by the molar mass, which was given 168.4 grams per mole. So that's how we go from this is much heat per this much quantity reaction that took place. We just convert to moles. So divide by 12.5 times 168.4 gives me a value of negative 71.6 kJs per mole. So that's the delta H of the solution process in units of kJ per mole for cesium chloride. One last thing is that this is just the reaction of this into water forming Cs plus Cl minus. The delta H of the reaction would be minus 71.6 kJ. So we can write the balanced reactions delta H2 because it's just 1 mole of cesium chloride. So I just multiply my delta H by 1 mole to get the reaction if we want the reactions delta H. Not ask for the problem, but if we wanted the delta H of the overall reaction of the solution process, we could write it out and then write the delta H accordingly. So we have the following reaction that is important in the, we're told it's important in the stratosphere. OH plus Cl2 goes to HOCl plus Cl. We want to know the delta H of that reaction, but I know these three individual reactions and their delta H's that are provided. Can I manipulate these equations? The idea of this is using Hess's law is, can I manipulate these three equations here such that they'll sum up and add up to my desired reaction? And so one of the things I can do is I could look for something like HOCl. I need 1 mole of HOCl in my reaction, and I see it's in one of the reactions on the product side, but the reactants don't match up right. Like this reaction here isn't exactly the same as my desired reaction, but I can see I need to cut that coefficient in half. I need to cut all those coefficients in reaction 3 by half. So let me write that out. That'd be 1/2 H2O2 plus 1/2 Cl2, just half a mole of H2O2 and half a mole of Cl2 would give me 1 mole of HOCl. Then my delta H for this reaction will be 1/2 times the negative 209 value provided in the problem. So I cut the coefficients in the reaction by half. I got to cut the delta H of that reaction by half. Okay, well, that's just one of the reactions I need to use here to add up to my desired reaction. So let me look for, so what I'm kind of looking for is I'm scanning my reaction here. I'm just looking for what's something that's only in one reaction. Like OH here is here, and it's not in any of the other reactions. And so I know then I'm going to need to take this middle reaction. I'm going to need to flip the reaction to get the OH onto the reactant side. So if I just flip the reaction, that would be to this one here. Oops, to OH to H2O2. So I'm just flipping that reaction. And I know that its sign will be the opposite of the sign of plus 134.0 since I flipped the reaction. If I flip a reaction, I flip the sign. And then I also need to cut the coefficients in half. So then I also need to multiply it by 1/2. So I need to take the original reactions, delta H, just rewriting the kJs a little more legibly. I need to multiply this by negative 1/2. Because I flipped the reaction, cut the coefficients in half. Okay, now if I add these two reactions up, I'm almost there, but not quite. So like if I add these reactions up right now, I'd be at OH plus half of Cl2 goes to HOCl, which isn't the desired reaction. I need a whole mole of Cl2. I only have half a mole right now. Well, that's where the last reaction comes into place. And then it'll also give us that last product that we don't yet have in either of these two reactions. I don't have the Cl, so I need there to be 1 Cl, so I need to cut that first reaction in half. So if I cut the first reaction in half, I'll have a half Cl2 go to Cl. So I cut the coefficients for that reaction in half, so my delta H will be 1/2 times plus 242. Okay, so what I'm going to do is I'm like mathematically almost adding these reactions up and then canceling out what's on both sides. So I have H2O2 on both sides, precisely the same amount. What else do I have? Well, nothing else. So everything else just adds up. So I have 1/2 Cl2, 1/2 Cl2. That gives me a Cl2. And then I have the OH. everything in this reaction was a gas. So I didn't take the time to write gas in, but in case you were confused, I could have been, or maybe should have been writing gas in for everything, but everything's a gas here, so there's nothing going on too crazy there. And then that goes to HOCl plus Cl. And so then if I can add these reactions up, then I need to add up all of these reactions that I've then turned the new delta H's into after I manipulate the equation. So I do a half times negative 209. I am very meticulous when I do this math. I do 0.5 or 1/2 times negative 209. And then I plus the negative 1/2 times plus 134. And then plus, I have a weird, so then I hit plus 0.5 times plus 242. I'm going to run through this again. 0.5 times 209 negative plus negative 1/2 times 134, and then plus 0.5 times 242. And I get negative 50.5 kJs. Is my delta H for that reaction. So Hess's law is like a puzzle. We just have to rearrange our given equations such that they add up and balance into our desired chemical reaction that we want the delta H of. And then we have to see, what do we need to do to those equations? Do I need to flip them and flip the sign? Do I need to double them, double the sign, double the magnitude? Do I need to cut the coefficients in half? So I need to see, how do I manipulate those equations so that they add up to my desired reaction, so I can know what the delta H is of that reaction. Common mistake in these problems is a lot of students think, oh, I'll just add all these up. Well, it doesn't work because those reactions don't add up to our desired reaction. So just treat these problems like a puzzle. Standard enthalpies of combustion of CO2 and water are given here. We're given the delta H of the reaction, and we're asked to find the standard enthalpy of formation of octane, which is this guy here. So my delta H of reaction is just equal to the sum of the products enthalpies of formation. So I have 16 moles times the delta HF of CO2 sum of the products, so I add 18 moles times the delta HF of water. So minus the sum of those of the reactants, so that'd be 2 moles times what I don't know, the delta HF of C8H18. And then this has a delta HF of 0, so I don't need to do anything with the O2. It's defined to have a 0 delta HF because it's the most stable form of oxygen at room temperature. And so all of this is going to be equal to negative 10,942 kJs. And so this is my unknown that I need to solve for. And so I just need to do some math. So I do 16 times 393.5 negative plus 18 times 285.83 negative. I get negative 11,440. So negative 11,440.9 kJs. Their moles have canceled. And then minus 2 moles times our delta HF of octane is equal to negative 10,940 kJs. And so I want to add this quantity to both sides. So I get plus 500.94 kJ. So I'm taking negative 10,940 plus 11,440.9. Be very meticulous with your minus signs. Don't do like just take negative this number and then plus 11,000. You have to add 11,440.9 to both sides to rearrange. And so that would be equal to 2 moles times the delta HF of octane. So I divide both sides by negative 2 moles. And so that gives me my delta HF. I divide by negative 2. Negative 250.5. kJs per mole. Problems are really hard if we ignore units. We don't see how we get kJs per mole out if we ignore the units too. Working with the negative numbers, just be very meticulous. Like every time you see a negative sign, I put the negative into the calculator. I try not to do in my head. I try not to keep track of the minus signs in my head because I'll make mistakes. My calculator is easier, in my opinion, on keeping the math straight and the minus sign straight. So I try to take advantage of the calculator. But so I get minus 250.5. So question 10, here I think this is the last question in our packet. Approximate the delta H of our reaction in kJs using the following bond enthalpies. So we're given the bond enthalpy of the triple bond nitrogen, the single bond hydrogens, and then we have nitrogen single bonded to hydrogen and another nitrogen in our product. And so using bond enthalpies, the way this process works is we calculate how much energy it takes to break the bonds in the reactants, and we figure out how much energy do we get back when we make our new bonds. So our delta H is approximated here from the sum of the bond strengths. V is a symbol for bond strengths of the broken bonds in the reactants minus the sum of the bond strengths of the sum of the bond strengths of the formed bonds in the products. So you're saying how much heat does it take to make 2 nitrogen atoms separated plus 4 hydrogen atoms separated? That's going to take a lot of energy. Then we're going to get back energy when we make our new bonds. Making bonds is always downhill in enthalpy. It's always exothermic to make bonds, and it's always endothermic to break bonds. And then a reaction where we have both bond breaking and making going on, it becomes a question of, does it take more energy to break the bonds in the reactants? And then do I get more energy out when I make the new bonds, or do I get less energy out when I make the new bonds? So we'll see. We'll see if the collective bonds are stronger in the reactants or products. They also let you kind of see that an idea here is that exothermic reactions that are overall downhill from reactants to products, are generally because we form stronger bonds in the products. So if we break weak bonds and form strong bonds, and we have a negative delta H here, and then if we break strong bonds and we form very weak bonds, and we usually have a delta H positive that's endothermic overall for the reaction. So it gives us a sense of that exothermic reactions tend to form stronger bonds than they start with. Endothermic reactions tend to form weaker bonds as they take place. And so in this case here, our delta H will be approximated by taking the sum of the one bond for nitrogen. So that's 1 mole times 941 kJs. I'm going to do that math in my head. So, or just get rid of the per mole just because I'm multiplying this by 1 mole of N2. And then the H2 is 435 times 2. So 435 kJs times 2 moles. And then, so that's the sum. I wrote a multiplication sign. This is the sum of the bonds. We add those up. And then we subtract the energy that we get back when we make the new bonds. So I'm forming a 159 kJ per mole times 1 mole. So I have one of those bonds for the nitrogen bond. And then plus, because I'm summing up the bonds formed, I have 4 NH bonds, which are 389 each. So I have 389 kJs times 4 for those 4 bonds, and just get rid of the 4. I'm just, I guess it's not, if I write out for one of these, we're just canceling out the mole in our head without writing out the per mole times the 4 moles. So it looks like I'm breaking some pretty strong bonds. So it takes 1,811 kJs to break the bonds in the products, and then I get back 159 plus 389 times 4. So I'm only getting back 1,715 kJs. So you can see I'm breaking stronger bonds and forming weaker bonds. And so my delta H is here approximated to be 1811 minus 1715. That's 96 positive kJs. So this reaction should be, we predict it to be endothermic because we're making weaker bonds and we're breaking stronger bonds relative to each other. The main idea, I think, here of looking at bond strengths is if you look at like H2 and O2 forming water, we know that's an exothermic reaction. Why is it exothermic? That reaction is exothermic because the bonds between H and O are stronger than they were between the two H's and then the O's and O2. So if you form stronger bonds, then that's going to be what leads to a negative delta H for that reaction. Okay, so that'll do it for this activity. Thank you for your attention.